ahead and record this one anyway. Okay. So, you guys said that the Alex assignment yesterday was hard.
Yeah.
I thought it might be. I didn't feel bad for you about it or anything, but I thought it might be. So let's talk about a couple more theorems and see if that might clear something up for you, okay? So, let's just start with this. Let's say, center of my circle right here. Let's say I have a segment that comes like that, and another one that comes like this, and they both go through the center of the circle. Then this would be a radius and a radius and a radius and a radius. If I were to multiply these two segments together, their lengths together, and multiply those two segments together, would I get the same number? Obviously I would, right? Radius times radius, radius times, it would work out, wouldn't it? Okay, so I don't think there's any question about that. The question is, what happens if the intersection of those two segments is not in the center of the circle? Okay, so let's just say we have one that looks like way the heck over here, and another one that's kind of coming like this. If two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. That's called the segments of chords theorem. Let me go through this. A, B, C, D, point E. The measure of AE multiplied by the measure of BE is equal to the measure of CE times the measure of DE. Can you look at it that way and see what's going on? That seem odd? I mean, neither of them go through the center. This chord's not even as long. This chord's longer than this chord. But when we multiply, look how short CE is. It's a small number, isn't it? So when we multiply it by DE, we get the same number as AE times BE. And this one, to me, you know how I said the other day, all these theorems, they just seem right. You just look at them and go, oh yeah, that's the way it looks. That's the way it should be. This one, I don't think that's the case. I mean, I can just put a chord in here any place I want, and then another chord in here like that intersects it. And this is X, this segment's Y, this one's W, this one's Z. X times Y equals W times Z. That, to me, I don't know. I have a hard time believing it sometimes. But that is the segments of chords theorem. You will not be asked to prove that one. Does that break your heart? No? You okay with that? Anyway, that's a good one. Okay. Let's see if this next theorem rings a bell from yesterday's assignment. Okay, so let's say they don't intersect in the circle. Let's say we got a couple of segments and they intersect outside the circle like this. Okay? A, B, C, D, and E. So these are secants, aren't they? All right. So AB times BC does not equal AE times ED. Like when they intersect in inside the circle, you just take the segments, multiply them together, works. That's not how this one works. Watch carefully. AB Everyone see AB? So that's the segment on the exterior of the circle. Okay. Multiplied by the entire length of the segment, AC, is going to equal the exterior bit over here, AE, times the entire length, which is AD. So when you have secants like this that intersect on the exterior of the circle, then you have that bit right there. So it would look something like this. This one's 9, this one's 11, this is 10, this is X. Okay, so we're trying to find X. So 9 multiplied by what? 20. Everyone get it? 9 multiplied by 20, the entire length. And then on the other side, what's the exterior bit? 10. And then what's the length of the whole segment? Okay, I'm going to put X plus 10, not 10 plus X. Is that okay? But those two numbers right there are equal. And can we solve that for X? Now, you have to put this in parentheses and make sure that you use the distributive property. So we have to say 10x plus 100 over here. And then, isn't this 180? Subtract 100 from both sides. What? What does 10x equal? Okay. And that means x equals 8. Let's see, does that make sense? Does 9 times 20 equal 10 times 18? It does, doesn't it? Okay, they work out. So that one is called the segments of secants theorem. So you have the segments of chords theorem. That's when two chords intersect. And since they're chords, they have to intersect on the interior of the circle. Okay? So this would be something like this one's 4, this one's 5, this one's 9, and this one's y. Could you guys find y in that case? Y times 4 is got to equal 9 times 5, doesn't it? Why does that work? You know, the proof of this one, I would have to teach you a whole lot more before you could understand the proof on this one. And I think once you did, it would you know, not be so bad. But yeah, segments of chords theorem, and then the segments of secants theorem right there. And then we have this other situation. We can have this other situation where you have a secant like this, and then you have a tangent coming from that point of tangency right to there. So let's say the secant's x. This bit outside here is 12, and on the interior right there we get that bit 6. What do you guys, any guesses? Say it louder. Yep, x squared equals 12 times 18. So just like the secant one here, you go the exterior times the whole thing, and then on the tangent bit you just go the tangent times the tangent. What if they're both tangents? We already learned that one, didn't we? Yeah? So if we have a circle and we have a line like that, I missed it. Okay, and another one, another tangent like that. AB, so that's a point of tangency. AC to a point. What do we know about AB and AC? They're congruent. Good job. Okay. Okay, did that help out at all on yesterday's assignment? Weren't there 2 or 3 of those? Yeah. Now you can always click on the little blue part and it'll help you out there, right? But I did not know I was going to be gone yesterday, so I prepared that, and I was going to give it to you today after we talked about this bit, but didn't get to it. So here's your assignment for today.